All right, today we are tackling a true classic, a problem that comes up all the time in system design interviews and in real world applications, the LRU cache. So, what's the challenge? It's simple to say, but tricky to pull off. How do you build a cache where finding data, adding new data, and updating the order of that data is always, well, instantaneous? We're talking O1 performance, and we are going to build it step by step.
So here's our game plan. First, we'll nail down exactly what an LRU cache is and the rules it has to follow. Then, we're going to try the most obvious approach and see exactly why it falls flat. But, that failure is actually what's going to lead us to the aha moment, the super elegant O of 1 solution. From there, we'll blueprint the design and wrap up with the key takeaways. Okay, first things first, let's get on the same page and clearly define what we're even trying to build here. What in the world is a least recently used cache? Think of an LRU cache as a small, really fast shelf for data you need to grab often. The key thing is, this shelf has a strict size limit. It can only hold so many items. So when it's full and you want to add something new, you have to make room. And how do you do that? You toss out the item you haven't touched in the longest time, the least recently used one. It's all about keeping the freshest, most relevant data close by. So the rules are pretty straightforward. We need two main functions. First, a get operation. This fetches an item, but just by fetching it, you're marking it as the most recently used. Then there's put, which adds a new item or updates an existing one. Either way, that item also becomes the new most recently used. But here's the kicker, the really crucial constraint. Both of these operations have to happen in constant time. We call that O1. It means the cache has to be just as blazing fast whether it holds 10 items or 10 million. And that, right there, is our puzzle. All right, we know the rules. So how would you start building this thing? Let's explore the most intuitive, straightforward idea that probably pops into most of our heads first. Let's just ask the most basic question. What's the simplest data structure we all know for just keeping stuff in order? Yeah, an array or a simple list, right? It seems like a no-brainer. We can just decide that, say, index 0 is the most recent item, and the item at the very end of the list is the oldest, the least recent. A new item comes in, we just pop it onto the front. Seems simple enough, but what happens when we need to grab something that's buried deep in the middle of that list? So, where does this nice, simple idea completely fall apart? Let's zero in on exactly why an array just can't meet that strict O1 performance rule we set for ourselves. And here it is. This is the fatal flaw. Imagine our cache has, 5,000 items in it, and we access an item at index 4,000. To make it the most recent, we have to move it all the way to the front, to index 0. Well, in an array, that means we have to shift every single element from index 0 to 3,999 over by one spot to make room. That is not a fast operation.
In that shifting operation, that's what we call O of n complexity. That n stands for the number of items in the cache. The bigger our cache gets, the slower this operation becomes. And that directly smashes our most important rule. And yeah, that's the bottom line. O of n is a total deal breaker. It's just too slow. So our first attempt, as intuitive as it was, just isn't going to work. We need a much, much smarter solution, one that can find and reorder things in the blink of an eye. Okay, so if the simple approach is out, what's next? Well, now we get to the really cool part, the aha moment. The solution isn't one single data structure, but a beautiful, elegant combination of two of them, each one perfectly covering the other's weakness. So let's break the problem in two. We have two very different needs. We need to find items instantly, that's one, and we need to reorder them instantly, that's two. How on earth can we get constant time performance for both of those things? And this slide, this is the entire strategy right here. Just look at how these two data structures are like perfect opposites. On one hand, you have a hash table, or a hash map, or a dictionary, whatever you want to call it. It's absolutely brilliant for instant lookups, O of 1. But it has no concept of order whatsoever. On the other hand, you have a doubly linked list. It's amazing for reordering. You can add or remove a node from anywhere in the list in O of 1 time, as long as you know where it is. But its weakness, finding a node takes O of n time. So one is fast for finding, the other is fast for moving. They are a perfect match. And that's it. That is the secret sauce. We don't have to choose one. We use them together.
We'll use the hash table for what it's amazing at, instant lookups, and we'll use the doubly linked list for what it's amazing at, instant reordering.
So, how does this actually work in practice? How do these two pieces fit together? Let's take a look at the actual blueprint for our high-performance cache.
Here's how it works. The hash table is our directory. It doesn't actually store the values themselves. No. Instead, for any key you give it, it instantly gives you a direct pointer to the node in our doubly linked list. The list's only job is to maintain the order. The node at the very front, the head, is our newest item. The node at the very back, the tail, is our oldest. So the hash table finds and the linked list orders. It's a beautiful partnership.
Okay, let's trace this out. Imagine our cache can only hold two items. First, we put key 1, it becomes the head of our list. Simple. Next, we put key 2, it becomes the new head, and it pushes key 1 back. So our list is now 2 through 1. Now watch this. We get key 1. The hash table finds it for us instantly. And because we just used it, we have to move it to the front. So the list reorders to 1 through 2. Finally, we put key 3. Uh-oh, the cache is full. We have to evict the least recently used item, which is the one at the tail, key 2. So we kick key 2 out of the list and out of the hash table. Then we add key 3 to the front. The final state is 3 through 1. It's like a perfectly synchronized dance between the two data structures.
So the get algorithm is just beautifully efficient. Step 1, look up the key in the hash table. That's O of 1. If it's not there, you're done. If it is, the table gives you a direct pointer to the node. Step 3, using that pointer, you snip the node out of its current spot. Step 4, you move it to the head of the list. Both of those are also O of 1. And finally, you return the value. Every single step is constant time. And the put algorithm is just as slick. If the key is already in our cache, we just update its value. And, since we just used it, move its node to the head. If it's a totally new key, we create a new node and pop it on the front. Then comes the important check. Are we over capacity? If we are, we chop off the node at the tail of the list. And, this is critical, we also have to delete that key from our hash map. The two structures must always be kept perfectly in sync. Okay, let's just zoom out for a second and quickly summarize what makes this whole two-part solution so incredibly powerful and effective. I mean, just look at the difference here. It's night and day. The simple array approach left us with O of n operations that just get slower and slower as our cache grows. But by combining the hash map and the doubly linked list, we achieve the holy grail, O of 1, constant time for both getting and putting data while the space just scales with the capacity. It's a massive, massive win. Now, a quick word of warning. If you ever go to code this up yourself, be super careful about these common traps. The #1 bug people make is they evict an item from the list, but they forget to remove it from the hash map. This creates a ghost entry and will cause all sorts of chaos later. Also, don't forget that updating a value is the same as accessing it. You still have to move its node to the head. The main takeaway here is just remember, the hash map and the linked list must always be perfect reflections of each other. You know, the key insight here is way bigger than just this one algorithm. This pattern, using a hash map for instant lookups and a linked list to maintain some kind of order, is an incredibly powerful technique that you can use to solve a whole bunch of other problems. It's an elegant solution to a very common challenge. So the question I'll leave you with is this: where else could you apply this powerful pattern? Thanks for diving in with me today.